One hydrogen state lasts a billionth of a second, but another lasts forever. Let's find out why. In today's problem, which apparently I don't know how to type, is 11.13, where we're tasked with calculate the lifetime in seconds for each of the four n=2 states of hydrogen. Hint: you'll need to evaluate matrix elements of the form 𝚡100x, 𝚡200, and 𝚡100y, 𝚡211, and so on. But remember that x equals r sine theta cosine phi, y equals this, z equals that, just the polar coordinate transforms. Most of these integrals are zero, and in fact, they pretty much are mostly zero. You only have two that aren't. So inspect them closely before you start calculating. You should be having flashbacks to 11.2 right now. And the answer that they provide us is about 1.0 or 1.60 times 10 to the negative 9 seconds for all except 𝚡200, which is infinite. Okay, so a lot going on here, but this is pretty straightforward, just a little messy. The reason why we care is clearly with all these zeros going to zero, with all these integrals going to zero, this is about the selection rules that we will see shortly. So the challenge for you then is, how does this relate to what was covered in chapter 6 with the vector and scalar selection rules and how they tie into the bigger picture, because we will have forbidden states being shown actually really soon. That being said, a lot of work in this problem, so if you want the PDF, comment for it and we'll send it over, or you can access it with the Patreon link below. Either way, you should keep it for your files. That being said, before we jump into today's topic, you should know I try to break down these complex physics ideas into more easy to digest pieces. If that sounds like something you'd like, hit the subscribe button and join us as we explore the universe. All right, so on to stop number one. Here we're trying to find the lifetime, which is tau. Now, what we had previously covered was getting the spontaneous emission rate. So we can find from the spontaneous emission rate what the lifetime is. So let's start by getting a general sense of what's needed here, which is essentially an extension of problem 11.2. To determine the lifetime of these various states, we need to calculate the spontaneous emission rate in terms of the electric dipole moment, where tau is the lifetime, A is the spontaneous emission rate given by 11.63 and 11.66 respectively, and the script P is the electric dipole. Okay, remember that the dipole radiation led us to a lot of things, and that's the source of the radiation that we see for the spontaneous emission. Okay, so since we're dividing by a fraction, multiply by the reciprocal, easy enough. Now we can plug in the definition for the electric dipole, which was Q, with the inner product of the position vector between the two states. Okay, now this inner product here, once we take the Q out of the magnitude, that becomes the heartbeat of this question. Okay, so what we should do is note that the inner product for the electric dipole is the biggest task in this exercise. So noting that here, psi b, psi a with the position vector can be broken down into x and the I hat, y and the j hat, z and the k hat. And thanks to linearity, we can split this up into three separate things. The reason why we want to do this is because when we investigate what happens on r, y, and z, that's where we have even and oddness in the integrands that we're going to integrate over. And since we're integrating over all space, that's negative infinity to positive infinity, most of them are going to cancel out, much like we saw in 11.2. So with that, let's go ahead and find out what these states are that we need for psi b and psi a and get to chugging. All right, so we're here midway through stop number one, so stop 1.5. This is still just getting organized in the setup before we can actually jump into the heartbeat of this question. So the states of concern here are the four n=2 states, 200, 210, and 21 plus or minus 1. Okay, and we know that these are the higher states. They're going to decay into the ground state. Okay, so n=2 needs to go to n=1. Makes sense. In problem 1.2, we already determined that all the matrix elements with respect to z, so we can just reference those, and we did that by examining the even and oddness of the integrand. So using the basic calculus result where odd integrands integrated over symmetric bounds yield 0, we can save a significant amount of time by repeating this observation process and checking which states are even or odd with respect to the inner product variable, i.e. x, y, or z. Furthermore, we can streamline this work considerably since the 𝚘100 is all real. We do not need to worry about conjugates, so the pairs of wave functions we need to observe the integrands are 𝚘100 and 𝚘200. So if we multiply this one and this one together, we get this thing. If we plug in the R definition, which is x squared, y squared, z squared, and then we see that and into the exponential, we see that x squared, y squared, z squared, those are both even in x and y respectively. Again, z we already covered in 11.2, so we can just reference that as needed. Furthermore, knowing that they're even here, that'll play a big role because when we multiply in the inner product with the x variable, that's going to turn that odd in the integrand. So very important for us. Similarly, the 100 and 210 states we see here. But because of the cosine, we need to reference how that is related to the variables here. So that's z and r. So we can go ahead and put them in. So here, again, we saw that this was odd in z. But again, since we have x squared, y squared in the integrand, or the exponential, excuse me, we know that we're even in x and y. So if we see that we're even here in the product space, or yeah, the function product space, then we're fine. Because that's going to cancel out very quickly, as we will see. Let's get to our last one, which is 𝚘11 and 2, 1 plus or minus 1. Okay, so from here, we see that we multiply across plus or minus on the phase factor for the E. We see that we get the minus signs moved around. And then by using this R sine theta e to the plus or minus I phi, which we had shown in 11.2, that gave us x plus or minus I y. Okay, so here, knowing that this r here is a square root, and then we multiply by x here and y here, we know that we're odd in x and odd in y. Okay, so this brings us through our setup stage, and we can go straight to stop number 2. But before we do that, drop a comment below about your thoughts with this theory, its selection rules, its ramifications. Let me know what you think, because I love hearing your interpretations and questions on it all, and it'll help me facilitate better guidance on future books and such as. All right, well, I'm just rambling now. All right, so now that we've determined the evenness and oddness of the wave function products, we can now we know that multiplying by the position vector, which is an odd function for each variable, results in odd integrands for the first two set of states, and an even integrand for the last two, represented by the plus or minus sign indicating the states. So given this, we can confirm that the matrix elements with respect to x and y are 0. So 1, 0, 0, 2, 0, 0 with x, 0. Y, 0. Then 1, 0, 0, 2, 1, 0, x, y, both 0. Well, that saved us a ton of time. Okay, and so the remaining matrix elements are now found via the integration. So that's 1, 0, 0, x with 2, 1 plus or minus 1. You see here that we multiply by x. And then we have the product of the functions here because we don't need to worry about the conjugates, things like that. X is not an operator like a derivative, so we're fine. Since we're in spherical coordinates, let's just go ahead and put our dv term here. Plug everything in, get them all separated, and clean this up pretty quick. Trying to color coordinate this as best I can. The exponential here from Euler's identity goes to cosine sine plus or minus I. Easy enough. But then the phi from the cosine here gets distributed, so that's why you have a square and a blue cosine there. We can put sine cubed there, easy enough. Then you have r squared, r here, so you have r to the fourth, and then the exponential. So we just separate them all out, bring all the constants out front as you would expect, and we see that we just have 3 separate integrals now. Thank you, Fubini's theorem. And now we can go ahead and chug these out by parts. Again, I would use an integral table to save you time, or Mathematica Symbol Lab, plenty of resource, but use them to your advantage. All right, so the phi integral, the cosine squared gave us a pi, cosine sine, that gave us an I times 0. Perfect, get rid of that thing. The theta integral for the sine cubed gave us a 4/3, and then we use a book, the chart in the book, or an integral table to find what this exponential integral is. So that was 4 factorial to a over 3 to the 5th power. And then we see just expanding the factorial and distributing the 5th power into each term. We can cancel out a lot. So 8 and pi cancel with the pi from this. 4 and 2 create 8, so they cancel. 3 and 3 cancel, and then this 4 can be turned into a 2 squared. So once we do that, we see that we're left over with the 1 over a to the 4th, but 4 a's cancel with 4 from this 5. So that's why we're left with a to the 1 here. This 2 squared can be added to this, so that's 5 plus 2. So overall, you get minus plus 2 to the 7th over 3 to the 5th a. Surprisingly simple, all things considered. Now we need to repeat this, but for the y variable. So rinse repeat, you see you get the same thing. Now y brings r sine phi sine theta instead of cosine phi. So distribute that into here. You see what you get there. No big deal. But we can rinse and repeat the theta integral and the r integral, so we have all our things here. But since we have sine, cosine, that part's going to go to 0. But so we have a plus or minus I here. That gets evaluated to pi. So we do have a complex number here, so just be careful. Much of the same cancellations happen here, and we can simplify this pretty quick thanks to what we saw in x. So cancel, cancel, simplify down. Here, plus or minus, negative times plus gives you negative. Plus times negative gives you minus. So either way, we're all minus, but we just have an I here. But we still get the heart here of 2 to the 7th, 3 to the 5th, all to the a. Okay. So with the integrals complete, we can now summarize all the results, including those found in 11.12 for the electric dipole. And we see that for 100 and r with 200, we get 0 for every component, so we just end up with a whopping 0 vector. Cool, we like that. Now we have psi 100 and 210, so we were 0 in x, 0 in y, beautiful. But the z that we found in 11.2 was given as this. We can just manipulate it, so we see here we get 2 to the 7th over 3 to the 5th, so we're just kind of putting it in this form, check there, just to make it easier for ourselves. And then further, we see here that with psi 100r psi 21 plus or minus 1, we get the x component, which is what we solved first. Then we get this y component, which we see here, plus this thing. So we get 2 to the 7th, 3 to the 5th, and a, and then we just have our components here. So now that we have that, we have found everything we need to for the electric dipole in terms of the inner product. So now we just need to take the magnitude squared. And this is back to the heart of the question. We need the magnitude squared for the spontaneous emission rate and therefore the lifetime. So going ahead and taking these things squared, 0 squared just gives us 0. Cool. Then we have this thing with the z direction, so square that, or take the inner product, or take the dot product with itself, whatever you want. Here, we see that that's going to lead to 2 to the 7th, leads us to a 14, but because of this square root of 2 squared, that's another one, so you get 2 to the 15. That doubles its exponent, so that's a 10, and then you have a squared. Remarkably, though, you're going to end up with the same thing here, because you have this inner product with 2 components, so you need the dot product, hence negative positive 1 squared, and then plus I minus I to the conjugate, and that equals a 2. So you see both of these things are the same value, which is remarkable actually, regardless of its geometric orientation, which is what the plus or minus 1 and L equal 1 states show you. So that's pretty darn cool, okay? All right, so this brings us straight to stop 3, where we can go straight to the lifetime. But, you know, what we saw last time with the numbers is that this illustrates a really cool picture. For all 3 of the L equal 1 states, regardless of the M state, we see how we have the same number for the electric dipole squared, okay, which is q squared, because you need the charge, a squared, and then 2 to the 15 over 3 to the 10. Very weird, but actually kind of cool, okay? And so clearly, we see that the lifetime of all these states, and since we're an electron, due to hydrogen, Q equals E, we have for the L equals 0 states, the electric dipole squared was 0, so we're dividing by 0, and that leads us to infinity. Okay, that's kind of wild, but it makes sense because you're stable there. Okay, so you're not going to expect some spontaneous emission. But now when you have L equal 1, you're not really stable in the same sense, so you're going to have some emission. And here we clean this up. We have a 3 there, dividing by a fraction, multiplied by the reciprocal. Clean this up. You see you get a whole bunch of constants, a whole bunch of crazy stuff here. That's just tedious, okay? So clearly, L equal 1 states are the star of the show, and if we wish to find the lifetime numerically, we need to bring in the Bohr energy, since this is a hydrogen atom, and we can do that via omega naught. But if you just want the symbolics, you have now found the lifetime. Clearly, we're interested in more than symbolic, so we want the numbers, so let's get to cracking on it. So, you know, in the opening statement of this, they said you can have a transition from the n equal 2 state to the n equal 1 state with whatever quantum numbers you want for L and M. So we're fine here. That being said, we need to be careful because that tells us that the 2 state starts in E equals 2, and then we go to the ground state, which is E1. Again, Bohr energy, this is the definition of omega, which is 11.18. The Bohr energy is referenced from 4.70, so 7 chapters back. You still have to use it. But since we have Bohr energy here, we know that E2 is equal to E1 over 2 squared, or n squared. And then we see that we have E1, factor that out, and then you have H bar, get rid of that. And then you're left with 1 over 4 minus 1, that leaves you 3/4. So then you can go back here, you can write that as negative 3 over 2 squared. Again, you want to do that because all these 2's that we see here, and then H bar. So let's put this all together and find a numerical representation, but beware, it's going to be messy because of units and things like that. Lots of substitutions, a lot of craziness about to happen, so get some extra paper. Okay, so clearly we're only focused on the L equal 1 states here for the lifetime because the other one was infinite, easy enough. So when we plug in our omega naught or our omega naught, realizing that's a cube, we need to plug in our energy values. So then we put the cube on every term. The negative sign doesn't go away because negative times negative, still a negative. So go ahead and simplify this down with all the cubes. We get that here, our new expression. Now realize that this dividing by a fraction, you need to multiply by the reciprocal, or you can just go ahead and minus away where you see fit. So multiplying the reciprocal of h bar, that's the same as adding 3 here. 2 is in the denominator, so when I'm dividing by 2 to the 6, that's the same as minus. 3 to the 3, that's the same as minus 3. And then this e cubed can stay put, easy enough. Now, upon simplifying that, we see that e cubed can be split up into negative e1 and then e1 squared. We do that for a substitution to get rid of some of these constants, okay? We know that E1 is related to the Bohr radius via h bar squared over 2 me squared. So a squared and a squared can cancel. A 2 here can turn that 9 into an 8. H bar squared can cancel and turn that 4 into a 2. And then we have mass E, which can go up here. Okay. Then once we do that, we can split them up into appropriate constants. So we have 3 to the 8th c cubed me over 2 to the 8th e1 squared. And then pi epsilon h bar squared over e squared can be turned back into the Bohr radius. Okay. And again, a whole lot of random substitutions trying to clean this up. You could absolutely go numerics right here and tidy it up, but that's a lot to chug in and plug away versus putting things in place now. So just be aware, lots of weird things happening in these simplifications. So once we get rid of that and substitute it in for the Bohr radius in terms of the mass and things like that, instead of the energy, we're fine here. This 4 is 2 squared, so that turns this 2 to the 8th plus 2. We have a pushed in there, and then me goes to the square there. We have to do that because now what we want is multiplying top and bottom by c. We want to do that in order to make c cubed or c to the 4th up here, so we can have an mec squared. And again, we want mc squared because that's Einstein's energy equation, and we want to do that because of the units of electron volts. Okay, we want to get rid of that. So by formatting and putting all this in there, all we really have is 3 to the 8th times A over 2 to the 10th times C with this unit conversion of electron volts. So E1 is 13.6 eV, but this mass speed of light equivalence brings us to 0.51 times 10 to the 6th. That helps us a lot in our unit conversion. So now that we, instead of plugging in every single value here, which is gross, we actually have something pretty simple with just a couple key substitutions. Again, not exactly evident when you first try this. I have pages of scrap paper, so definitely don't feel weird if you have to run in circles, because I did. That being said, we can plug this in. Calculators don't like these sets of large numbers, so Mathematica would be a preferred method there, or Python, depending on your level of curiosity and coding. but nonetheless, we see that we get about what they have. With rounding, I get 1.595 times 10 to the negative 9 seconds, and they got in the opening statement 1.6 times 10 to the negative 9, so very close, very compelling, and that was a journey. That was actually really fun. A lot of selection rules that we will use instead of just showing even and oddness, which is a geometric argument, they get formalized with the vector and scalar selection rules. So why would I go through this trouble when I can just say, oh, look, these states don't mix, so they're forbidden, and I can get rid of them? And we will see an example of that very soon. All right, that was fun. And if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I just want to take a moment now as well to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to create these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. If anyone else is interested in supporting the channel, join our Patreon community. You can check out the link in the description below. Together, we keep exploring the wonders of science and discovering even the more amazing things. Especially, what was your thought on the Nobel Prize, by the way? I know I asked about it on a post, but it still seems like it's spurring people up. So feel free to join the discussion. That's really what the goal is here. Provide more intermediate stuff and help everybody along the way. And of course, I grow and get to revisit things, so that's fun. As always, thank you for watching, and until next time, stay curious.